In this lecture, we are going to introduce some new topological spaces such as T1 space or regular space and normal space. Let's begin with a T1 space. Let me give you a definition of T1 space, and after that I will provide some example. So here is a formal definition of T1 space. A topological space X is said to be a T1 space. A topological space X is said to be a T1 space if for any pair of distinct points of X, there exist two open sets which contain one but not other. So this is the formal definition of T1 space. A topological space is called T1 space for every pair of distinct points in this topological space X. We should have two open set. Each open set contains one of the point but not the other. We can also rewrite this definition like this. In other words, a topological space X is said to be a T1 space. It's said to be a T1 space if for any two element X, Y in X such that X and Y are different, there exist open sets U and V such that X is in U. If X is in U, then Y should not be in U, and if Y is in V, then X should not be in V. So you can see here topological space X it's called T1 space if for every for any two distinct element in X, let's call those two distinct elements X and Y, we should have two open sets U and V such that X is in U but not Y, and Y is in B not but not X. So also we can describe this definition of T1 space using this picture here. Let's say this X is a topological space and we have two distinct elements in X. Let's call them X and Y. Then we should have two open set. Let's call one of them is U that contains X but not Y, and then also we should have another open set, let's call that B, which contains U not X. U and B is not necessarily they have to be disjoint. I mean, if they could be disjoint, but it's not mandatory U and B they have to be disjoint. The only the important point is if X is in U, then Y should not be in U, and if Y is in B, then X should not be in B. If there is a topological space that satisfies this property, then that space is called T1 space. Let me give you one simple example of T1 space. Here is our first example. Let's consider the set of real number R with the standard topology. Consider R with the standard topology, then the set of real number R is T1. It is a T1 space. Okay. If we are considering standard topology on R, you can see it is easy to see this why R is the T1 space in the standard topology. In standard topology, each open sets are like those open interval. Okay, let's say this is our real line. This side is positive infinity and this side is negative infinity. Now, if if R is T1 space, then if we pick any two distinct element, let's say these are the X and Y. If we take any two different real number, then there should be open set containing X and Y such that each open set contains one of them but not the other. And it is easy to construct such open set. Like I said earlier, in standard topology, open sets are simply the open interval. So to construct those open set containing X and Y, so what we can do here is we can find this distance between X and Y. The distance between X and Y, that's gonna be Y minus X, and you divide that guy by 2. Then what you do is you go to the left side from X by this distance. Let's call this distance is a D. Then and also you go to the right side of X by this distance. Let's say you are here. Basically this is the midpoint here. Then that's gonna be X minus D and X plus D. So this is open set containing X, and obviously you can see from this graph this open interval does not contain Y, and that's our first open set containing X. And to find the second one, now you do the same thing. Okay, you go to the left side from Y by this distance D, and that's gonna be Y minus D, and you go to the right side by the same distance D. The right endpoint is going to be Y plus D. So this is our second open set containing Y, and obviously it doesn't contain X. And this one is our first open set. Let's call this is U, and this one is B. So we found two open set U and B containing X and also containing y respectively, but u does not contain y and v does not contain x. That's why R is T1 space. Okay, so this is very simple and it's popular example of T1 space. Now I'm going to give you a theorem without proof, and that theorem gives us a very simple characterization of T1 space. Theorem without proof. So this theorem will give us a very simple description of T1 space. A topological, and here is the statement: a topological space X is a T1 space if and only if every singleton subset, singleton subset means those 1-point subset of X. Every singleton subset of X is closed. Now you can see this theorem has a very simple description of topology of T1 space, and this is if and only if condition. If every 1-point subset of a given topological space is closed, then that topological space is T1 space. And also if you have a T1 space, then every singleton subset or 1-point subset of that space is closed. So we can use those we can use this property of topological space to check whether it is T1 space or not. Let me give you one example related to this theorem. Let's call this is example number 2. Consider a topological space X whose elements are A and B. Consider this topological space with the topology tau, whose elements are empty set, whole set, and the singleton set A. Okay, now let's use that theorem to check whether this X is a T1 space or not. So by this theorem, this space X is T1 space if every 1-point or every singleton set of X is closed. Now let's see. Let's find the closed subset of X here. Then the closed sets in X are, so this closed sets in X under this topology are those subset of X which are the complement of each element of this topology. And if you take the complement of empty set, then that's gonna be the X. If you take the complement of X, that's gonna be empty set. And if you take the complement of A in X, that's going to be B. Okay, so these are the only closed subset of X, which are whole set, empty set, and the singleton set B. But the other singleton subset of X, which is A, is not closed. Okay, then by that theorem we can say that X is not T1 space. It is because if it is T1 space, then it has to have every singleton set closed. We just saw that this singleton set B is closed, but the other singleton set that contains A or that has element A is not closed, so that X is not a T1 space. Since this singleton set is not closed, so X is not T1 space. Okay, and next I'm gonna talk about regular space. Okay, let me give you a definition of regular space, and then I'll give you some example. So here is the definition. A topological space X is said to be regular. It's said to be regular if per each pair consisting of a point X in topological space X and a closed set if for each pair consisting of a point X in topological space X and a closed set B, and a closed set B disjoint from X. B is disjoint from this element X, means X is not in B. X is outside of the closed set B. If for every pair of a point X and a closed set B not containing the element X, there exists disjoint open sets containing the element X and the closed set B respectively. Okay, so this is the definition of T1 space or topological space X. Not the definition of T1 space. This is the definition of a regular space. A topological space X is called regular if for each pair of a point X and a closed set B not containing this point X, we should have disjoint open set containing X and B, containing that point X and the closed set B. If we can find such open set for every pair of point X and the closed set B not containing X, then the space is called a regular space. Okay, let me describe this definition using this a picture here. Let's say X is a topological space and we have a point X here and a closed set B here. Okay, now you can see here the point X and B, they are disjoint. Set and point disjoint means that point X is outside of B. For each pair of those X and closed set B not containing the point X, we should have open set. We should have disjoint open set, not the open set. We should have disjoint open set U and B such that one of them, let's call U, contains X and the other one B contains B. If we can find such open set for every pair of such a point and closed set, then we can say that the topological space is regular. Okay, now let me give you example of regular space. Example, let's consider this set X, or this topological space X, whose elements are A, B, and C, with the topology tau, whose elements are obviously empty set, the whole set X, and the singleton set A, and then 2-point set BC. So here we are considering topological space X whose elements are A, B, C with this topology. Now, here we want to check whether this X is regular or not with this topology. So if you go back to the definition, so to check whether this X is regular or not, what you need to do is we need to first find the closed subset of X here. Okay, let's find those closed subset of X here. So observe that the closed subsets of X in this topology, they are basically the complement of each element of this topology. Observe that the closed subset of X are, so if you take the complement of empty sets, that's gonna be X, and if you take the complement of X, that's going to be empty set, and complement of this singleton A, that's gonna be BC, and the complement of BC, which is going to be A. So these are all possible closed subset of X. Now we want to check whether this X is a regular space or not. So this X is regular if you pick any point of X and a closed set disjoint from that point, then we should have a disjoint open set containing the point and then containing that closed set in X. Okay, let's consider the point A and then closed set X. So X is not disjoint from A because X contains A. So we don't need to check whether we can find U open set containing A and X here, because A is not disjoint from X. Phi, or the empty set, is obviously that is disjoint from the point A. So here we should be able to find open set containing A, not just the open set, disjoint open set containing A and the empty set, and it is and we can find those disjoint open set. Empty set, it contains in itself, so the open set containing empty set, that's gonna be the empty set itself, and then this open set or this singleton will contain will contain this element A. So our disjoint open sets are empty set and the singleton set A, and they are all disjoint, and also A is in this singleton and the empty set is in empty set. So the condition of regular space for the point A and the closed set this empty set satisfies. And it has to satisfy for all the closed set. Okay, and now let's check this A with the other closed set, this one. So A and this closed set, they are disjoint, so we should be able to find the empty set, disjoint open set containing A and this closed set. And you can see here this guy and this one, these two are disjoint open set, and this element A is in this singleton and then obviously this closed set is inside this set. So A and this closed set BC also satisfy the condition of regular space. Uh, and the last closed set is this singleton set A, but this A and this closed set, they are not disjoint. That means A and any closed set in X satisfy the condition of regular space. And also we need to check with B and C, and if you check the condition for B and the closed set, they will also satisfy. And if you check the condition for this element C and any closed subset of X, they will also satisfy the condition of a regular that we have in our definition. So we can conclude that X is and hence X is a regular space. X is a regular space. Okay. But here also we can see that X is not T1 space. If it is T1 space, by the theorem that I provided earlier, if X is T1 space, all the 1-point set, they have to be closed. But you can see the 1-point set B or singleton set B is not in the list of the closed set, and also the singleton set C is not in the list of the closed set. That's why this X is not the T1 space. Okay. On the other hand is regular space, but on the other hand, X is not a T1 space, since the singleton set sets B and C are not closed. Okay, so from this example we can see that regular spaces are not necessarily T1 spaces. Okay, we have an example of regular space which is not T1 space. That means regular space, if you have a regular space, it may not be a T1 space. Okay, next I'm gonna give you a definition of normal space and example of normal space, then we done with this lecture. So here is a formal definition of a normal space. A topological space X is said to be normal if for each pair, a topological space X is said to be normal if for each pair A, B of disjoint closed sets of X, a topological space X is said to be normal if for each pair A, B of disjoint closed sets of X there exist disjoint open sets containing A and B respectively. So you can see here in this definition, a topological space X is it's called normal space if for each pair of disjoint closed set, for each pair A and B of a disjoint closed set of X, we should be able to find disjoint open set. Let's call them U and B, such that one of the closed set is in one of the open set. Okay, that means, let's say if A is in U, then B has to be in B. If we can find such disjoint open set for every pair of disjoint closed set in X, then we can say that this topological space is normal. Okay, let me describe this definition using a picture here. So here, let's say we have a topological space X. We have a topological space X, and let's say A and B, these are disjoint closed sets in X. Then this X is called normal space if we can find two disjoint open set. Let's call one of them is U and the other one is B. They have to be disjoint such that one of the closed set is in U, let's call it A, and the other one is inside B. If topological space X satisfy this property for every pair of disjoint closed set in X, then that topological space is called normal. Okay, now here is an example of normal space. Let's consider a set or topological space X whose elements are A, B, and C with the topology tau, whose elements are empty set, obviously the whole set, and let's call the singleton set A, singleton set B, and then we have this 2-point set AB. Okay, so we are considering this set X with this topology. Now we want to check whether this X is a normal space or not. To check whether X is a normal space or not, first we need to find all the closed subset of X, and then we need the disjoint closed subset of X. So let's first find the closed subset of X here. The closed subsets of X are, so these are basically the complement of each element of our topology. Complement of empty set, that's gonna be X, complement of X, which is the empty set, and if you take the complement of this singleton set A, that's gonna be BC, and if you take the complement of the singleton set B, that's going to be AC, and then complement of this singleton set, which is C. So these are all possible closed sets in X. Now to check whether X is normal or not, we need a disjoint closed set, and you can see the disjoint closed set. So BC and AC, they are not disjoint. BC and C, this is not disjoint, and BC and X is not disjoint. So it looks like if, let's say, if F1 and F2 are two disjoint closed set in X, then one of them has to be empty set. Okay, otherwise this F1 and F2, they cannot be disjoint, because to check whether the space is normal or not, we need to disjoint closed set. So it looks like in this example, so one of those closed set is going to be empty set, otherwise those two sets are not going to be closed, because the if you take those other four closed set X, B, C, A, C, and C, they are not mutually disjoint. That's why one of the closed set has to be F1. Okay, just let me write down this thing. And if let's say if F1 is the empty set, then F2 it could be any other set. It could be X, it could be BC, it could be AC, or it could be C. Now we need and now we need to find the disjoint open set containing empty set and the other set F2. And it is easy to find those disjoint open set. We can take those open set is an empty set and then the whole set X. Empty set and the whole set X both are open and they are disjoint. And this empty set, it contains F1 and the whole set contains F2. No matter what is F2 here, we have option for F2. It could be X, this one, or that one, or the singleton set. Say, no matter what is F2, this open set X contains F2 and the empty set contains F1 because F1 has to be empty set. Otherwise, is not going to be disjoint with F2. So we found those two open set. That's why we can say that X is a normal space here. Okay, let me just write down the thing that I just described here. If F1 and F2 are disjoint closed subsets or disjoint closed subset of X, then one of them say F1 must be empty. Must be empty set phi. Hence, empty set phi and the whole set X are disjoint open sets such that F1, which is inside empty set, and F2, which is inside X. Hence, therefore, X is, so therefore, X is normal. So this is an example of normal space here.